It is my pleasure to invite our first speaker, Mr. Enosh Gurung, to deliver his presentation, and then after he completed, then we can continue to the second speaker, and then after that, we will start the Q&A session. So, Mr. Enosh, the screen is yours.
Thank you so much. Thank you so much. Good morning, everyone. It's a great pleasure to be here with you all. Okay, so my name is Enosh Gurung. I just graduated from Mudak University on Master of Engineering Practices, major in Environmental and Sustainable System Engineering. So I'll start with my presentation today. Okay. So do I need to share my screen for the presentation or? Okay, my presentation is not coming up. Do I need to share my screen for the presentation?
Can you share? Is it possible? Or maybe the organizer can share it for you?
Yeah, I think I did.
You cannot? Okay, Maria, can you please share Mr. Enosh's presentation? Or is it okay? Actually, I have your presentation. Maybe I can share it for you. Wait. Okay. Geopolymer. Okay. Yeah, I can share it for you. Wait.
Okay, thank you for that one.
Yeah, just say next, and then I will click.
Okay, sure. Thank you. So today I'll focus on how geopolymer concrete enables a circular construction system by replacing high carbon binders and waste-driven materials. This talk will examine the science, the environmental impact, and the relevance for Indonesia and the region. So next slide, please. Yep. So the construction sector consumes enormous material. So, and if we continue the linear model, that is extract, manufacture, use, and dispose, one day we'll run out of the natural resources. So in this way, the circular economy comes into play. The circular model maintains resource loop. This shift applies directly to civil engineering because our material become part of long-term infrastructure. The diagram shows the Allen MacArthur Foundation Circular Economy Butterfly Diagram. On the left, we have the biological cycle, and on the right, we have the technical cycle. So, cement carbon burden. Cement produces 8% of global CO2 emission. Can you go to the next slide, please? So 1 ton of cement produces around 0.9 ton of carbon dioxide. One fact is Indonesia reduced its cement CO2 intensity from 725 to 614 kg of CO2 per ton from 2010 to 2020. This improved lowered emission per ton, but the total national emission rose because of production was increased. Next slide, please. So geopolymer concrete avoids the clinker entirely. It uses the fly ash, slag, and other aluminosilicate sources activated by sodium hydroxide and sodium silicate. The reaction forms a NaSH gel that binds the aggregate together. Next slide, please. Geopolymer concrete touches every circular economy loop. It reduces the carbon emission to up to 80%. It reuse the fly ash, the ground granulated blast furnace slag, rice husk ash, and it recycled the construction and demolition waste into new concrete. We can recover from the construction and demolition waste, and we can redesign durable structure with longer service life. Next slide. So the raw material for the geopolymer concrete is we use the fly ash that we can get from the coal power plant. We use the ground granulated blast furnace slag, which we can get from the steel manufacturing plant, and rice husks from Indonesian agriculture. These are the geopolymer blinder that we use. And activator chemicals are standard industrial output already produced locally. Next slide, please. So the reaction mechanism. Portland cement hardens by hydration, which relies on water reacting with clinker minerals. For geopolymer concrete, hardens by polymerization, where alkaline activation dissolves aluminosilicate and reorganizes them into a dense three-dimensional network. This fundamental difference explains the superior durability and lower carbon footprint of geopolymer system. Next slide, please. So this is the OPC hydration versus the GPC polymerization. So in OPC, they produce high CO2 footprint. In GPC, we don't have calcination, and which drastically lowers the carbon dioxide. Thank you. Next slide, please. So the mixed design variable. So the mixed design depends on several variables, like the more concentration of NaOH, sodium silicate to sodium hydroxide ratio, and curing temperature, and also the alkaline to fly ash ratio. There are many paper published on the mixed design of geopolymer concrete, and from there we can find out that the molarity of NaOH is kept between 8 mole to 16 mole, and ratio and sodium silicate to sodium hydroxide ratio is usually kept around 2 to 2.5, and curing temperature is kept around 60 to 80 degrees. So geopolymer concrete shows better resistance to chloride, acid, and sulfate than OPC. Shrinkage is lower, permeability is lower, and service life is longer. So an Indonesian marine exposed beam studied with high calcium fly ash found room temperature cured geopolymer concrete achieved higher compressive strength and higher resistivity than seawater cured specimen, supporting field durability potential. Next slide, please. Yeah. For environmental impact LCA, life cycle assessment shows that 60 to 80% carbon reduction with geopolymer concrete. Energy use is lower because the clean is eliminated. In Indonesia, fly ash utilization remained below 1%, representing unused potential for it. Next slide, please. So infrastructure application. Geopolymer concrete already appears in precast panel, paving blocks, retaining wall, marine structures, and even in 3D printing. This application aligns with Indonesia infrastructure need for flood resistance and coastal durability. Next. So one of the real-world geopolymer concrete application can be seen in the Brisbane West Whale Camp Airport in Australia. It shows major proof of large-scale GPC durability and performance. Next slide, please. So as I told earlier, GPC touches every part of economic sustainable economy. So industrial symbiosis converts waste into continuous material loop. Fly ash becomes the binder becomes infrastructure, and demolition returns the material as aggregate. Nothing leaves the system. Next slide, please. So the main challenges remain in raw material variability. In one of the research showed that the fly ash that is found in Indonesia contains high calcium, so we have to modify it for the betterment of the geopolymer concrete. And another one is we don't have standard for geopolymer concrete right now. So because of that, the people don't use it much, and there is low public awareness for geopolymer concrete. Next slide, please. And for the research and innovation, advancement now focus on solar curing, hydrogen power plants, and BIM LCAA integration and AI optimization. Mukherjee's work in Murdoch University so rice hulk as based sodium silicate work as a circular activator, strengthening Indonesia's local potential. And for the future, we net zero concrete pathway for 2025 to 2050 depends on eliminating the clinker. So geopolymer systems are among the core alternatives in global and ASEA roadmap. Indonesia's industrial ecosystem is already positioned for adoption. Slide, please. Geopolymer Geopolymer concrete converts industrial waste material into infrastructure, reduces carbon footprint, extends durability, and closes the material loop. And I'll end with the line: if concrete build the modern wall, geopolymer concrete can rebuild it without a carbon cost. Thank you.
Okay, thank you very much, Mr. Enos, for the insightful presentation. Now we're going to the second presenter.